you doing? Welcome to Southern Savannah, another of our equipping videos that we talk about industrial machinery that you can start with that can actually do a lot of production and you can have it even in your garage. Now, in this video, let me just put a disclaimer. The eye you see here is just a bar fight. Do not include that. But I'm just going to put these glasses on so that we talk about what we're talking about today. So what we have here is a CNC plasma cutter. You've heard of CNC, meaning computer numerical control. One mind may think about that machine behind me, which is a CNC router. This, however, is also CNC, but not a router. It's a CNC plasma. A CNC plasma cutter basically cuts metal. That's what it does. Anything that conducts electricity is cut by a CNC plasma cutter. Now, we're going to go more into detail as we train people, but I'm just going to run you through the video so that you understand a bit of what we're going to talk about here. All right, to start with, anything that is metallic, you're going to cut it here. Depending on the amperage you have on your plasma cutter, it will affect the thickness that you can cut. We have a 60 amp plasma cutter here. Plasma cutters, unlike lasers, are measured in amperage, whereas lasers, you measure them in watts, right? So this is a 60 amp plasma. I can do comfortably 6 mils mild steel. I can do stainless steel, 4 to 6 mil more or less. And I cannot do any composites that have non-metallics inside them. Like your aluminum die bond, I won't be able to work with that. However, a few things to understand. You have a Z-axis, up and down, which is your torch that controls the height on the material and also controls the torch that you use to cut everything. Now, your torch is getting a couple of things. It's getting air that's coming from a compressor that is right there. And it's important that my compressor does not have water or moisture. So you put air dryers in between. More of that in the video as we explain. Now, secondly, another thing that it has is it has the connection to my power supply, which is this is where the power is coming from for the plasma. And as you can see, when I increase here, I go all the way up to 61 and of course down all the way to 0. You set your amperage according to what you're trying to work on. Now, another important thing is the earth clamp that I'm going to use. My clamp is the negative charge. The air that's coming in there has a positive charge. So when I clamp this, I complete the circuit, and that's what makes plasma. For those of you that do not know, plasma is the fourth state of matter. Solid, liquid, gas, yes, there's also plasma. They didn't teach you that in primary school, did they? Now, to move from there, I have to always clamp my material. Ideally, I could clamp my bed. Clamping my bed also works, but if my material has a coating, I'll continually get a short circuit, not a short circuit, but an incomplete circuit between the positive charge coming out of here and the negative charge that I have here. So normally we clamp the material that we're cutting, and we always clamp outside the cutting area. From there, you're going to see my CNC control unit, which has different movements, of course, where I can move it sideways and forward. I'm going to do this, and you can see my axis moves. This is my x-axis. On this machine, it's a 1.5 meter length, which is with x-axis, and a 3 meter axis as we go down there. It might be 2 meters. I'll double check on that. Right, so we have y-axis and x-axis, and then z-axis is simply the torch that you see up and down. That's what 3 dimensions mean, right? When we say we're in a 3-dimensional axis, we mean x, y, and z. So that's your x, your y, and your z. We do say that it's a 3-axis machine in terms of movement, yes. However, in terms of what you're cutting, you're only doing 2D shapes because you cannot, with a plasma cutter, control the depth as you can with a CNC router, which is right behind me. Okay, cool. Another important component is I talked about the air compressor, which brings air here, comes out from there, the electrode, which clamps the material, your CNC unit, which controls your x-axis, y-axis, and your z-axis, which is up and down. This is the screen where any job I put, I'll be able to read it from here. We'll have a separate software tutorial for everything. But let me just show you some flames just for you to understand. You have a couple of things. You have air running, which if I press an air test, as you will see here, air on, you hear there's noise there. And then a plasma beam, I'm going to touch it. That's what a plasma beam looks like. Fascinating. All right, cool. So in this video, we're going to talk about everything. Changing the consumables, doing basic cuts, and the sensitivities that you need to look at, the machine, your oiling, and all of that. So all good. Stay tuned. Cheers. You understand what this is, and CNC plasma cutting. You have 2 meters on your x-axis, 3 meters on your y-axis. This is your screen. If I turn it on, let's start from the side. You see all the controls there. Now, I don't want you to get confused. This is not a complicated machine at all. It's basically 2 separate units that are combined. One unit is a CNC unit, which is this thing you see here, this arm and this arm. So that's Y, X, and then this. But then you get this guy here, this small thing at the top. These are now the plasma components. So what makes it a CNC plasma is the CNC component plus the plasma component. It would be easier than a laser cutter, but laser cutters like this, where the CNC system stays the same, but you simply plug in a laser tube and it becomes it. Easy also to come a router. One reason it's not a router is simply because the router has a lot of traction as compared to this. So this one you can see for you, which like it's not that robust. Why? Because there's no need for it. Because the plasma never has to touch and fight with the material, unlike a CNC router. Right. So I'll explain from the power supply, then I'll come to the CNC unit. From the power supply, I'll start with this. Whenever I say plasma power supply, we mean this. It is the plasma power supply. The maximum you have on this, we measure plasma cutting in what we call watts. Sorry, it's amps. Yeah, laser will use watts. Laser will use amps. I think the maximum I've seen that I've worked on, there are those which go a lot higher, but I've worked about 230 watts per watt. Here's the basic concept. Power supply, yours goes up to 60 watts, to 60 amps. With 60 amps, you can cut as much as I think you're looking at it. 6 mil might still without a problem. Different power supplies at the same power can give you different results. So what I mean is there are plasma units called something like hypercam. A hypercam at 45 amps can cut 9 mils for you. Perfect. It's an American make of the same thing. This one, to match a 45 amp, you have to be double. Yeah, so that's also, a lot of people say, no, there's no quality in plasma. I don't know if you've ever heard of it. I mean, if you've heard of that accuracy, there's more accuracy in a laser cutter than a plasma, of course. But even while staying in plasma, you can do a lot more by simply changing the power supply. Another way to overcome that is getting a higher amperage power supply. That means if your cuts are not clean, all it's telling you is, look, I'm putting way too much, or I'm staying way too much on this part for you to be able to cut. So the metal is melting before I can have a clean cut. So what you do, you just get something higher. You go to maybe and it simply fits. Everything else stays the same. We simply change the box. Yeah, but this is good enough for now. 60 amps. What you're doing is, with plasma, how you're cutting is very straightforward. You have a positive charge and a negative charge. The positive charge is very straightforward. You're saying, you saw the direction of the head. I'm going to do the 2 changes with you so you understand. But what we're still saying is, we have a positive charge that we're getting from the plasma. When you press, it sends a positive charge. Then the air comes in to push that positive charge. And then you have an head clamp, which is here. We normally clamp the material or the table, just depending, but it's normally safer to clamp the material. Until you're cutting full length, it becomes tricky to clamp the material. Why? Because it gets in the way of the job. But ideally, clamping the material is the most sure way. So the material is just your negative charge. You're completing a circuit. That's the whole point. You have air pushing positive pressure, and then you clamp it to be negative on the other end. Which means you're going to see air that's going out air. The first reason you get an out air is because your circuit is not complete. Actually, that's the only reason you get an out air. Your circuit is not complete. So your circuit will be complete because caused by many things. First thing is the head clamp. If there's any cut, or if maybe I'm clamping the table and there's a bit of a short circuit before we get to the material, I also get an out error. So let's say now I'm clamping the table, which means the material should be reacting to it. But because this one has paint, you might see that you can get an out error because of the coating that we have here. Yeah, exactly. So it's clamp paint, number one. So we're going to clamp the material. Maybe someone can do that for us as we can plug it just finish the material. So that's number one. We supply A through here. That A is the same A that passes through your plasma torch. So the A is coming from your compressor. You're looking at 4 to 6 bars. Now when I say 4 to 6 bars, you set it like this. You don't set 4 bars before you run the A out. You set your 4 bars once the A is coming out. Because remember, if I set 4 bars now, and then I turn the plasma on, when the A starts coming, it's going to drop to 3 bars. So I have an undersupply of A. So normally I set 5 bars, so that when I turn it on, I'm going to lose about a bar when it comes to 4 bars. Or you can set 6. You see it getting. So when I'm done, I just lock it. So it's up, not too much force, and then I put the amount of air that I want. Is the compressor still on? Yeah. Okay, that's fine. Once I get to maybe, for me, I get to like 5 bars and then I clamp. Your air allows you to have a cleaner cut. Your air also pushes the charge. So remember, sometimes you struggle with a lot of process because you don't have enough air. And if you don't have enough air to a point where you have 4 bars, sometimes you're going to get an arc error because your charge is not to the negatively charged plate. So fast, sometimes. Are you guys sure? Did you get me, Jason? No, which part did you? Okay, come. Slow. There's a scale there. You can see it. It's 0 up to 8 bars. If you lift that thing there, you can rotate it. Clockwise increases and anti-clockwise decreases, yeah? There we go. So clockwise increases, anti-clockwise decreases. Do you get it? Does it make sense? Are you guys straight? You can rotate the thing, my guy, don't worry. I know it feels like it's going to break, but it's not going to break. You see? Right. You get it? Make sense? So once you put your air, you do what's called an A test. If you go to the front of your plasma, you're going to see there's a button written A test. You press it and you check that side if air is actually coming out. Or you don't really have to go, you can hear it, but if you want to be sure, you can just put one guy and put the end there and press, you can press A test. Do you see it? A test. A on. Sorry, A on, yeah, sure, that one. Press it. Keep pressing it. You see? That's an A test. A is coming out. So for me, how I set my A actually is, while I'm pressing that, that's when I adjust the knob for A. And then I set it while this air is coming out, so that I know that when it's cutting, I have a consistent stream of 5 bars. You get it? Because you don't want to lose air. Remember, the compressor at some point releases all the air and it starts pumping again. You don't want to lose that air when you are halfway through the job. It's an expensive piece, sometimes with 16 miles to the function. So it's really important how you set your air and that you test it. Once your air is coming out, then the next thing, okay, but you understood everything at the back. There's only A in power on and off. That's all that's it. Are we good here? At the front, you have a couple of connections. Connection number 1 is, of course, the F clamp. Your F clamp can get loose. That happens a lot. For some reason, it's not a very tight fit. It's tight now, but I don't know how, it doesn't lock in. So, if it gets loose to a point where it's just shaking, you're going to get it in a right. Are you with me? So always check your F clamp. Number 1. Number 2, the other connection you have is, you see this connection, number 1, this is your electrode. Then number 2, this is the A, which is going through. So the A comes in the back, comes in from the back, and then comes out of the front, comes out at the front. So this is your positive charge, this is your negative charge. This is A. Going to get, that's all that's in the front.
So that thick pipe is A only?
Yeah, this is A only. Nothing else on that, just A. Are we together? Mm-hmm. So plasma cutting, you're cutting with electricity. A negatively charged plate, positively charged beam, it cuts through. It's A, very simple. If I demystified it, it's straightforward, right? Okay, cool. So now that we're here, you know everything that's there. Let me talk about consumables and how to change them before I come to CAC.
consumables and how to change them, these are the things we use to cut constantly, right? So the things we use to cut, you get a tool like this. You can use any spanner if you ever not find this. But ideally what I do is one of the main tasks I give is measure this and make multiple copies of this. This is your tool changing tool. You need the actual measurement. Normally, the supplier sends you with the correct measurements, but we can always measure ourselves and try. So here we're going to talk about, you have, this is your tool changer that you're going to use, sorry, your consumables changer is the tool you're going to use. It has 3 sections, one for the electrode and another one for the nozzle. Those are the main ones. And apart from that, you have what you call a nozzle. Everybody can just get a piece and then check it out. The nozzle is what allows the air to get through. So the nozzle, basically it allows the beam that you're passing through and the air. The nozzle has this surface here. Do you see there's a hole on it? For each amperage, when I say amperage, you can get a 45 amp plasma, 60 amp, 80 amp, 120 going up, right? Each amperage, the more the amps, the wider the beam. Number one. So when they say plasma is not accurate, part of the thing they mean, the tolerance gets wider. Why? Because the thicker you're cutting, the wider. So which means if I'm cutting something that's 6 mil, I'm losing about 2 mil. It can get to as far as 2 mil, sometimes 1 mil of the opening here. Okay, so this is your nozzle. Your nozzle is simply to guide the air and to also guide the beam. So which means as your beam, remember you're pushing fire. The fire is actually burning this thing here. So your consumables, this is it weighs out. But the most crucial of your consumables, I'm going to try to change it, I'm going to show you. Of these, you have 1, 2, 3, right? The first one you're going to work with should be the big one. You simply put it here and hold the torch in position. And then you can loosen it. Once you loosen it, you're good. So this is the current one that's there. And as you can see, this hole is actually bigger because the more you cut, the more you finish the consumable. Now consumables are like this. People can ask you, oh, how long does a consumable last? It depends on what makes it. There are consumables made of a rougher steel, of a tougher steel than the other ones. The thing with plasma consumables, they're quite affordable. You can get 20 of these for under 300 rands. You see. Whereas if you want the maybe tungsten carbide or the much higher grade, they'll be more expensive. So people sometimes don't see the reason to go expensive on these. So that's your electrode. Do you see what happens? I mean your nozzle. Do you see what happens when it's working? It finishes. So these are things you constantly have to be checking. Are my consumables still intact? Number one. Number two, the second thing you look at, I'm going to move now. I'm going to go to the second section of my tool. And there we go. Guys, did I get the correct truth? Okay. Got it. Okay. There we go. And this is your electrode. So your electrode also gets finished as you use the machine. Maybe you can do an up close of the used and an unused electrode here. And we'll check it out. I'm going to show you guys there's one that is also used here. Just not sure what it is. Okay. So do you see that this plate here, it's flat, right? And as you use an electrode, this flat part is going to become like a depression. It's going to become like a tiny hole. As long as you're not getting any arc error, don't worry about changing any consumables, because quality-wise, it's not like a page where you can see that there's a big. No, it's not a big deal. We change them when you get an arc error, but I'm showing you what to look out for. Can I have the used one? Perfect. Do you see what happens? If you get arc error and you open and you see that the size don't really matter, but if you see that there's more, it keeps getting open, it keeps getting charged, then you know that I have to change my electrode. So these are things you need to keep space of. Now I'm going to have someone feed it back and then we conclude the part on the consumables. There was a ceramic cover that was here. Can I get stuff to put it up? Yeah. And you can put this one back, it's still fine. No, we were putting the used one. And then the electrode.
Yeah, so right.
Okay. You saw how it goes up. You just need to find the right angle for this part, and then you can put this one back. Is it tight enough? Because remember, if your electrode is loose, it's going to be losing air and it's going to give you an arc error. It's tight. It's tight. Okay, sharp.
He almost broke the nose of that guy.
Okay, cool.
Tell people of the EFS before.
But anyway, the last thing you'll find in which you'll find it is just it's simply a ceramic shell. So all it does is make sure that all the, remember sometimes you get water splashes if you have the water, all of that. It protects the situation. Nothing causes it. But it's not a big deal on cutting because a key thing which we're now going to talk about when we talk about functionality. We have 3 axes, right? Z, which is the up and down of this thing. The Z axis is purely controlled by this thing. It's called a THC, torch height control. That's this, the standalone unit, right? And then you have the X, which moves in this axis, and the Y, which is that whole box there. Okay. So to start with the X, you see this torch has a lot of freedom. If your torch is Q, you're going to get, and it's very easy to not notice, you're going to get a lot of dross when you cut. So normally people take, I wouldn't say a spirit level, but just a ruler to put it down just to make sure that it's straight, because it's very hard to use your eyes to measure. Some people use this near thing, but even still, how do you measure just using your eyes? So number 1 is that. And another thing, it normally gets offset because it does what is called initial height sensing, where it comes down, that is the material then goes up. So every time it does that, if it's not tight enough, it tilts this thing. And when it tilts it, you do your whole job and you wonder, why do I have to clean up and what after? Because of this. So you just take an Allen key right here, make sure you lock this as tight as you can. This is normally found here, but this button, let's make it as tight as possible we can. Alright, with that being understood, you're going to see there are a lot more holes here. Well, it's just the motor to raise this up and down. It's just the communication for this to tell it when to go up and when to come down. These holes are for what they call oxy-acetylene. Some people cut with electricity. Some people cut with gas. If sometimes people want cleaner cuts, actually use gas, oxy-acetylene. It can go a lot thicker. So if with electricity with this system here, with 60 amps I can do 6 mils. With oxy-acetylene I can do double that. Using gas. We're not talking much on that today, but these are options that people use as well, and you have the capabilities here. Same torch, you use a different torch, but then these are the outlets. The machine is capable of handling that. Always make sure you're greasing these tracks. Here and also on the bed. Because what's going to happen is the more you cut, those metal flakes are going to be going in. And if you don't spray it regularly, it's going to be jamming. Alright, cool. Is it getting boring, guys? Yes, yes. Now we're here on the system, but does it make sense? So far, any questions? Is the machine confusing at all? It makes sense, right? As long as you not change your consumables to control your air, it's good. The thing on the plasma system is how to control the areas that you have. You see, if I bring it here, it's going to max at 61 or 62. And then when I drop it, what's the lowest you're getting? So you have that range from 0 to 60. The concept here is the same concept as train. If you want your parts to be deeper, you need more power. So the thicker the material, the more the power. Straightforward. But you also don't want to be using too much power when it is unnecessary. Why? Because your consumables finish faster. So you're now balancing between speed and power. So if, let's say, I'm cutting something that's what, 0.9, 0.6. So that's 0.6. I don't need a lot of amperage. Normally, anywhere from 30 to 25 milliwatts. You get this is 25 watts. What unit is this? Amps. So when I say amperage, I simply mean that, right? So 25 amps is what we're going to use. We can increase it because there's no right value. You can easily cut this with 50 amps and it's fine. But the thing is, if you use more power, you are exactly. So it's the power speed there that you're doing. 25 amps at a speed that can cut through. If I put too much speed, what's going to happen? It's not going to cut through. However, with plasma comes the issue of what we call dross. You see this piece here? Did you cut it here, right? No. So you see, they give you a clean piece like this, and you would assume that every time it cuts as clean as this. No, not always. Sometimes you cut and you're going to see a lot of dross finish, like a lot of, yes. So do you see this? You see the differences? This one is very smooth edges. This one was actually cut by lazy. But anyway, it's marketing. But do you see there's a bit of an overlap? Yes. That's what normally happens when you cut it with plasma. This is very common, these simply called dross. We don't eliminate it, but we can minimize it. Sometimes the cuts are good enough. Sometimes the thicker the material, the more dross we're going to get. We're not making hospital grade equipment. Exactly. So that's the good part. But to clean it is very easy. So you just wait for it to cool down, and you literally just hammer it off. It's basically flaking. The problem happens while it's still hot, you try to remove it. You're not going to have an easy time. So you just leave it cool. It won't even take 5 minutes to cool down. Once it cools down, normally people put, that's why I was talking about the working area. You find maybe a large stone or something to heat it on, where you just take it, just heat it with maybe normally I use just a small hammer. It will just etch off everything and then you're good. But if I cut this on low speed, I will get more dross. Because the beam of energy is spending too much time on one spot. Let's bring this to cutting and melting. In this case, are the same thing, but I don't want you to think of them as the same thing. You don't want your material to start melting before you cut. In as much as cutting is melting in this regard. But I mean, the more time you spend there, then the surrounding metal, which you're not intending to cut, starts melting. So which means by the time you finish the cut, that melting, that slag hangs on and then you have a lot of dross. So to minimize the dross, you want higher speed. But for you to achieve higher speed, that's how you raise your power. So you get the balance. It's the power-speed combination. So you lower your speed, you can cut deeper. But however, if it's too slow, you get a lot more dross. So which means you're doubling the work time because you're going to have to spend a lot of time finishing the work. So sometimes that's how people, you find, why are you using 40, 50 amps to cut something like, because they know that it's after work if I use less power. Are you with me? So far, we're together. Okay, last thing on testing this is what is called the plasma test. If you just press, I'm gonna leave this system here. Don't worry, this system basically just means mesh cutting and manual cutting. So your manual cutting is fine, don't worry about it.
Hello?
But the A test, sorry, this one is for testing the plasma beam. Once I see the case, you just press this and then you see the check. You see that always you need to get the check before you start cutting. So after you put,
Yeah, can you press? Someone next to you.
alright. Okay.
That's also
So that's pretty much it. Plasma cutter, there's nothing much more. And what we explain now is everything to do with the power supply. And anytime I say power supply, I mean this. I don't mean that. That's just a voltage regulator. It's not part of the machine. You're just using it to make sure the power is stable. Okay? Do you have any questions on this box? It's just an on and off switch. Now here, let's talk about the system. On the side, you can come through, you see 1, 2, 3, 4, 5, 6 functions. To start with, the first thing is the image of switching. Something is happening and you don't know what to do, you're panicking. You just keep the image installed. Once you hit it, nothing is going to be able to. The machine is a turn off, but nothing is moving. And then you simply press it to turn it back. From here, you see you have this button. So, put your hand here. Press this button. I want you to tell me what you feel. Press it. Press it down. You hear there's a discharge which happens here. I do this. So basically this is for manual movement. It allows me to maybe I quickly just want to move it to a certain position. I don't want to press the buttons and run and be checking what you just simply, or I normally do it to do what's called an area check. Before I start cutting, if I put a few sheets, check your area. Don't ever make the mistake of not checking the area. Because what happens, the material we use is expensive. But the main reason is not even about saving material, it's about saving your life. These things are dangerous, more so here. But this thing, if you don't check, something can just go loose and it can damage someone. Bits here can break, go straight into your eye, that's it. You're not getting it back. People can lose fingers. So you just want to be very careful. And just to demystify a lot of stuff, people think that if I put my hand there, I will be hurt or something. No, not really. You're not gonna do. The moment you put your hand there, it's going to be an accident. Right away. Because it can't pick up because it won't conduct electricity. So you're fine. Okay? No one. So Jackson, you can put your hand there. Alright. Okay. So I've explained this for the manual. So the area check that I need is normally I move my whole arm outside. Okay. Once I come here, I say, okay, where I'll be starting? Somewhere here. I'm happy. Then I say, I go the full length and then I start coming back. This is why I said you can't have these machines in the same area. It's not even an issue of not using them at the same time. You can see it's already in the way, right? And which is actually going to help because now imagine during the problem, it's there, this gear is bent. Normally this arm, you change the whole arm. It's very tricky once it gets damaged. Another thing is your box here and the ear pipes. These things actually get hooked a lot. So what I do is I normally like to take some masking tape and you just make them one thing so that you don't get anything to hook on anyway that then damages a lot of things. So if I bring it all the way, as you can see, these are all the things you check in the area just to see when I put my full sheet, I don't want any errors. Are my cables long enough? These are also some of the things we check. Okay, all the way up to here, and then you cut through. Here's one thing you may or may not know. Your machine is fixed to 1.5 meters, yes, but it's not fixed to the length. You can go up to 12 meters or even longer if you want. I've seen the longest I've seen is 12, simply by upgrading this. So what they simply do is they sell this unit separately. You can see it has gaps here. And so you just buy these ones and then you get another one of these. Then you just keep on going and you can cut as long as you want because this thing doesn't know when to stop. Actually, it doesn't have limit sensors. On some CNCs, but this CNC doesn't have any limit sensors. So basically, let's say I want to move it, keep moving. Oh, sorry, still move. Is it on manual? Let me see. Step continuous, yeah. It just moves, which is to tell you something. It has no locks. They did not think of that. So you might want to find something to just put for locks because you don't know who's operating. Just one day someone makes a mistake. It won't know. It'll get here and it'll jump off. It'll fall. Maybe your job just went over by 10 centimeters. That's enough for you to just get out of gear. It rolls off. So those are things you have to look at. Some people look by the gear, some people look by the track. Okay, those are good. Those are important things to note. All right. Apart from that,
I'm now going to show you the movements. So you understand how we move it manually, right? You see now, I can't move it manually because it's engaged. Yeah, the moment I do this, it's disengaged, and I can move it manually. Very good. This is the on and off switch. Red is off, 1 is on. From there, you have your plasma. The plasma is this box here. That's your power supply. So this is what communicates the CNC unit with the plasma power supply. Remember, on its own it's a CNC, but it becomes a CNC plasma when you involve this mandala, yeah, of course, and the torch head control, but mainly this thing. People can use this thing on its own, manually. I'm sure you've seen people cutting on it. This is the same thing you can use. Okay, number 1. So that's 1. Number 2, this is the arc voltage. This is what goes on to communicate with that. So these are the 2 connections coming from here to communicate with this thing. And then lastly, you have your control, which goes to the control arm from the up and down. This is power. So there's no confusion here, right? All the cables are in. If ever you have any issues on any connection, you should be able to communicate and know which cable is getting an issue or whatever. These are all the cables that you have. Engage this is disengage the motors, this is engage the motors. Are we good here? Anyone wants to try anything here? Straightforward? Okay, sharp. One.
So you can actually the starting point minor.
Sure. That's the whole point, because they realize that pressing it and waiting for all that sometimes it wastes time. Yeah. Okay, cool. So remember, we use a coordinate system that doesn't matter, but our 0, 0 normally for CNC machines we use bottom left. Anytime, whether it's there, whether it's here, even this is your bottom left. So bottom, I mean here where I am, and then left. So we start from here. This is 0, 0, which means to move to my right, am I pressing Y positive or Y minus or X positive or X minus? What am I pressing? Yeah.
It's going to be, if this is your X, it's X positive.
Can someone press X positive? Let's see. Don't press yet, just look at your buttons. Okay, this doesn't write X positive, but there are arrows here. Up, forward, back, sideways. So let's move it sideways. There we go. And it's a continuous move. Stop it. So if you want to cancel that, do you see that you're pressing it, it keeps moving, it doesn't stop. If you read your screen, this is where you just need to understand. These machines are very simple if you understand the screen. Can I have a recording of the screen? Your screen is very straightforward. It tells you F manual continuous move. Press F again. Let's see something else. F keep moving. Keep moving simply means as long as I'm pressing it, it's moving. As long as I'm pressing it, it's moving. When I release, it stops. Press F again. F step. Step means it moves a certain step. I can put it to say just move 5 millimeters, and then it will move 5 millimeters. Press it and leave it. So that's the step which was set. And how do you set the step? So you can see now if I keep pressing, it's not. You see it's shaking because it's moving per step that was set. You're not really going to be using much of this function. I want to spend time on the things you're going to be doing. But if you're interested in, but these are not functions that are crucial. But the main thing you'll be using is 2 functions. You'll be using a continuous move, which is this one, and it keeps going. But normally that's why we disengage and then we move manually, right? But ultimately, we normally leave this one on. This is the safest position to keep it on key, so that it only moves when someone is pressing. That way it doesn't fall off. Are you with me? Okay, so moving it forward, you know, moving it back, you know, sideways, you know, right? The last thing is the Z-axis, which is the up and down. Up and down is there. You control up and down with these or these. It's all up to you. It's all up to you. So let's say we bring it here. Can you have different right? From here, you're going to do this is where these are the job parameters now. There are 2 things. There's what is called torch height sensing, and then there's the height that you use. The height that you use for cutting is the same thing as when you're printing. Remember, for a printer, the printer has to be a certain height from there. Otherwise, if it goes too high, you get an overspray. Too low, you get smudging. Same thing with this guy. You're looking at about 3 mils on top of the material. How do you set that? You see this button is written IHS test. Press it. Yeah. And leave it. You see that? You're never going to get good quality cutting, number 1. Number 2, your electrodes are going to finish very soon.
because it's scratching the material. That's also another thing. The warping of the material. So you need to balance both of those things. With metal, the thicker the metal, the easier it is. It doesn't warp. But the thinner metal, you have issues with. So you see that height there? That's the height it is at now. Press it again. Let's check. Now remember when I said it loses position, it's because of that touches and also that kills that motor a lot because of that hole. Pressing, because it doesn't just do it when it starts. Every time it's cutting, at any point it gets to a corner, it has to sense, okay, I'm here. Then so anytime it's doing what they call entries and exits, which you're going to do on the software, it has to sense the height because it understands that metal bends. So at every point it has to keep on just checking, are we still at the same height? There is another way that it can do that automatically. However, it's not a perfect system, but that is called, we use that as sensitivity, right? If you see here where it says arc setting, let's see. Hold on. Okay, it's good enough. All right. If I turn this off, the sensor is off. If I turn this on, the sensor. So the sensor is just an electrical feedback that tells this thing every time it's moving. You say, you're getting too close to material, go up, come down, up, come down. So the height that we set first, let me show you. You see this bar here that you press for the up and down, it's small. If I increase it, say to 69 when I press, check something. You see that? It's now higher. Much higher. If you drop it to 0.2, there you go, press it. There you go. If I feel like that height is enough, cool. So how do I know if the height is perfect or not? Apart from just thinking that it's supposed to be 3 moles or 2 moles, you simply check your dross. If you are getting a lot more dross on the top, when I say dross, we're together, you know what I mean. If you're getting a lot more dross or that on the top, it means my torch is too high. Are you with me? Where's that plate that I have? Okay. Yeah, it's fine. Give me that one. So let's say I'm cutting. If at the top here, there is a lot more of this dross here, all I should know and understand is, my torch is too high. So the beam, by the time it touches the plate, the part of it that is concentrated is already finished, the focal height of it. Or if I'm getting a lot more dross at the bottom, where I'm supposed to get dross, but what that also means is maybe it's too low. So I just want to focus it enough that it is in the center where there is all the beam concentration. Are you with me? That's how I minimize or decrease the dross, which is what we're about to test now. Okay, so with that, let's drop it to 0.15. I think that would be ideal.
Thereabouts. And then this one now controls the sensitivity so that the torch knows when to go up and when to come down if the material is warping. It's controlled there. It's the basic voltage. There's no set value here because it depends on the material you're using. A coated material will be very hard to change because there's no push signal coming up. Whereas something like this is easier to change. So I'll leave it at 130 to start with that, and then 125 and then but the higher it is, the more sensitive it is. It's basically it's on the electrode. Yeah, it's on there. So it is just sending signals. Say, look, I put the negative charge there. Is my potential difference the same? The moment it starts feeling like the potential difference is changing, then it tries to maintain that potential difference and maintain it according to the IHS. All right, cool. So sharp, we're going to do a basic cut, just like a small circle. You understand everything else here, right? You can make your design on the computer and send it, but this machine has what you call a preset library of basic shapes. And I don't want you to get confused. It's a very simple machine. If you read the screen,
you will find your answers. First, I want to find a small circle. I'm going to look at where it says shape library. Do you see it? Press it. So just every button here just aligns here. There you go. I have a primary set of shapes. And then I can choose which shape. So if anything I want to cut is already here, there's really no need for me to go and design it and then bring it back here. Are you with me? Okay. So let's take a small circle. There we go. And then it has three things that it asks you. Lead in, lead out, and size. Basically what lead in and lead out is check that cut there. Do you see that there is a small arc at the beginning? You see that? And then there's another, so it's like a loop. You see, like that semicircle there. Right. Let me explain what that is to you. This will define the quality of your cuts massively. The whole point here is there's an entry point where the machine starts to cut. So it pierces, see that IHs that you did there, pierce, and then it enters here, then it gets in and starts cutting. It doesn't come back, it just enters here to mark the height, then it starts cutting. It goes through the whole shape. Once it's done, it doesn't stop it, it comes out here. Why? So that it can give you a full piece which doesn't have entry and exit marks. You get it? That is your lead in and lead out. You can determine the lead in and lead out by the length that you put for the lead in and lead out. Sometimes you can make it a straight line, because on spaceship sometimes you don't want to be an arc, it can just be a straight line. Where instead of, imagine, see this dot here, if you had put it in line with the circle, you're not going to get a perfect circle. You understand it? So that's why it does it outside. So you need to understand, do you need the male or the female of what you're cutting? Do you need a stencil or do you need a cutout? Because if I needed the outside, then my lead in and lead out was supposed to be inside. Do you get it? So now my lead in and lead out are out because I needed the plate. That's being cut out inside. Are we together? Okay. So with that in mind, I've told you what to do. Now tell me what you're going to set here. Lead in and lead out. You set it out. See? Perfect. Outside, inside. So let's set it outside. Okay, good. And secondly, the length is just how wide it is. So this 10 is simply that.
Does it have 2 days of set it inside?
Yeah, outside.
No. Look at the. If you want it outside.
Oh, sorry. Yeah. Okay, read the screen. Yeah, but sometimes it's lost in translation because a lot of these things are written in Chinese and they just translated. Ideally, it would make sense for them to say outside, means it's outside. Yeah, but
when you say inside, you need the inside part.
I think this is what they mean.
Yeah.
To them, I would say you need the inside part.
So if it's outside part, you need the outside part. So this one goes inside. So you need the outside part.
Perfect.
So in this case, the outside is scrap. When you want the inside.
Yeah. Makes sense so far? This 10 millimeters is the diameter of this small circle that you're going to use here. Don't worry, this thing can be peeled off, so right? You're not sweat it. Alright, cool. So this is just, you want this to be big enough to accommodate. Okay, so if it's too small, then the piercing will be too close to the material edge. So it won't have an effect. So you want it big enough to be, but also not too big to a point where you waste the material. Yeah, so let's start with that 10 millimeters. And then the size of, which is the diameter of there. But this size is not fixed to diameter, just depends on what software you're using. For some systems like this, the size actually tells you 1. Size 1 is not the diameter. In this case, it's the radius. Sometimes you find it just be able to read the screen, it will tell you. So you can see here. So now it tells you 200, which means this is a 400 millimeter circle that is cutting. You can define it. Let's say we want something that's just 20 centimeters wide. What am I going to put here? These are millimeters, by the way. You can put it. Make sense? Keep in mind where the dot is. A lot of people forget that. And they make the mistake of putting 0, 0, 0, 0. The problem is,
it's fine, but your machine won't know. So it's going to go, lose the arm, and drop. And that's why you really have to be careful. So you find where the spot, and then you can put the full stop here. Put the dot. There you go. There we go. Now you can put it, doesn't matter. Does that make sense?
And if you didn't put the dot, you just press enter.
If you?
If you don't put the dot, you just press enter after putting enter.
Oh, yeah. Same thing. So good, yeah. But you get the point, right? Okay. So now you understand the size, you understand the lead in and lead out, which are the piercing points. And the piercing height, which is set here. The sensitivity height, the sensitivity value, which is here. So far, so good? Okay, perfect. I'm happy. We're happy. Now, with here, read your screen. Where do you think we're going to go next? Just read your screen. Enter. F8. So that's the thing. If you press enter, it's not going to respond. Read F8, enter. Yeah, there we go. Now we're good. We have a material. Next thing, we need to set the starting position. You can either move this thing with your hands, or as I like to do it, just going to raise the torch a little bit, disengage it, and then bring it somewhere. We said it's how big? 200 should fit somewhere here. So your origin is always at the bottom left. Always. So let's say if I do this, will it be 200 today? I won't make it, eh? My fear is that. So let me do this. It's exactly here. Like at the corner here. So you're just placing it just so that you have 200 and 200.
So the diameter of your job is 200.
Yes, the diameter of the job is 200. Are you good? Once you're there, you disengage it. Right. So you've disengaged, but you haven't yet set the position in the system. You set it manually. So in the system, you now have told us that, hey, listen, this is my 0, 0 position. How do you do that? Read your screen F8. It's written F8, 0. Do you see it? Right, there you go. Press it. There we go. It's a new 0. I want you guys to understand something. If I disengage these motors and I move this anywhere else, and I say start, it's not going to come back. Because it's still written 0, 0 here. Do you get me? But if I had linked it with the buttons, I could have been able to say return to, or it would come back. But because I didn't put these measurements, because I was moving it manually. That's something to keep in mind when you're doing this. Okay, so I brought it back here. I'm going to disengage it, 0 it again. Now use.
Can I ask you?
Yeah.
I can see when you were moving it with the buttons, it's moving it from the. Does it mean that's our 0? Or our 0 is.
No, it's moving from the starting point. That's where it's going to start. Our 0 and where it's going to start are two different things. Our 0 just sets limits to say you can start wherever you want. We don't care because it thinks according to which one is the most motion. But we're guessing this is where the shape ends. That's what we're saying. So now that you've set the X and Y, but you have not set the Z. Now let's set Z. IHS simply means initial height setting. So you can set the initial height. There we go. There's the tricky part. So what do you do? Because remember the material is rocking. So are you sure that the material is going to stay like that? Or how it, for me, what I normally like to do is get that within the material is a lot harder. If the material is going to stay like this, if I know that the material is going to stay warped like this, then I set my height while I'm holding the material to make sure that, I set my height on where the on where I have the sling, so that it doesn't push it down when it's setting its height. That's very important. It seems like, but that's the most important thing for your quality. Because if I set it now, this is an untrue height. Because when it cuts, it doesn't use this, it uses this. So set your IHS here. Just move it here. Back a little bit. Just align with this so that they support and a little bit back. Okay. Now set just use it.
No, you just press it to set. Much better. It's still down. There's no winning music. Alright, press it again. A little bit more. Again, sorry. Alright. Now if you start, it still remembers this position. You can see that's why it's offset here. But I'm ready to start. My A is reset. Did I check my amperage? Are we good? The minimum amperage we normally cut in here to minimize water and all of that. We normally cut them over here. Yeah, but you can use any amperage. It's a good, we checked everything and we're about to start, but there's one thing we haven't talked about. You guys, what's that in there? We've done the A, we've done everything, the height, but there's one thing we haven't talked about. No, not really. That you can only check once it's cutting. But do not think about speed. Your cutting speed is important. So your cutting speed, you find it there. See, you have the F was for setting the more type of movement, right? That distance on the tape, those 5 millimeters, you see there, is huge. So if I wanted to move, let's say 100 millimeters every first, so then now every step will be 100 millimeters.
Yeah,
does that
what
make
you're
sense?
saying.
You get it? And it goes right to 100 millimeters. But what I'm talking about now is the cutting speed, X cut speed.
You can send it through this one.
2,400 millimeters per minute on this one. That's what it is.
Yeah,
So ideally what you simply do is you press
Which one
X and then you set your speed. Let's start with 2,000 and see how it goes.
You can't see most of the material.
Okay. Well done. From there, can you reset your XY? I wanted to do the whole. So reset the XY.
There is polycotton, there is setting, there is a pony.
Because it's in as much as we set as it before it starts, it's going to do that here. Right. So everything has been set, let's try cut.
Yeah, but setting is shiny. Cut will first start.
Yep.
Set.
What does the screen say?
Yeah. Show to cut.
Are you sure?
Okay.
So what do you
maybe
think?
choose polycotton.
Enter would make more sense.
Okay, then it's showing me my time.
Cut error.
122,000 here.
Is my compressor on? It's direct color. Okay,
And how much time do we have?
My height sometimes goes right. Like I'm just going to do something now. Okay, cool. Now it works like that. Because you can't use the center stick. How do you tell? Yeah. Exactly. You must know your material limits. Yeah. So, yeah. So I've set. Yeah, now it makes sense. It's just good to when these kids set up. Sometimes they never run production, so they never really know some of the things. Okay, fine, that's that. Apart from that, I'm still getting hot here though. I just need to check it up a bit. I'm gonna up my IHS a little bit to 3. Let me see. Okay. Let's start. So you see, wherever it is, if I just say start. I didn't reset the starting position. Let me bring the starting position somewhere. Let's escape. Okay. So let's say I want to start here now. And then F8 being the 0. Don't worry about the edges, I've set it already. And start. Enter. Let's see. How did I calibrate the X? Break alarm again. Okay. What do you mean calibrate the X?
Like to move it from there to there.
For the starting position.
Starting position.
It's just I went into the system and I told it that you knew your home with the bottom left position. So it doesn't matter now. Whatever you do, it's always going to. Yeah. How I did it, maybe it's good that you asked. Let me show you. I simply see as long as we're in this menu and we don't see any settings, we are in the job menu. We want to get out of that. So I press escape and say quit cutting. Yes. So now I'm out of the cutting menu. I'm here. And I come to part options here, and then I choose starting position, and then now I tell it center would be F1, F2 is left back, which is this one. You can either do that or just use the buttons here. That's why it's clear, right? Most of the stuff is very clear. You can even just, and even if I want to change the size of my shape, I can just come to edit file and all of that. Once I'm done here, then so you have to get out of the settings menu for you to do all of this. So again, it's escape always to, now that you once you see your shape, then you can start. It's going to remember all the other settings that would set. I just want to find out though, why do we keep getting that arc error? Enter. And how did we get there? No, it's not going to cut there. Not going to cut there. You saw something was wrong. Yeah, set your piece.
What's that?
Okay, no. I'm just saying how it means 0. F8 to not 0. Okay. Yeah. G cut return offset. No, we're not going to offset cutting. Okay, it's still continuing with the previous piece. So cutting return. Let's enter. That's the thing. This thing wasn't calibrated properly. Yeah, it's cutting when it's moving because it was simply coming to the. Okay, that's okay. It was an offset.
Doesn't it mean that the axis that are not moving?
No, it was the offset. Okay, so let's do this. Let's cancel this job entirely. Cancel it by simply pressing escape. Enter. Right. Press escape again. I want to see something. Okay. Now, with this system, let's try and get our job again. So let me just enter here. 100. Everything is still the same. Inside. Cool. Perfect. Right. Now let's 0 X and Y. Good. As long as when I 0, this value doesn't change, it's still reading that I'm inside the last job. It hasn't cancelled. It hasn't cancelled the last job. Setting point is still there. Change it. Part option, yeah. Step point, yeah. There we go. Cool. Set it. Yeah. So good. Set already. No. There was no need to escape. You're already fine. Now you can start. Okay. Enter. Enter. The PS point, don't worry, it can determine that on its own. It's way too high, but it's fine. There we go. Does it make sense so far? Well done. Two things. You need a pliers always. This one doesn't matter, it's not hot because it's thin. But the thicker material that you cut is going to be hot. So people will be so excited to take it out, and then when you take it out, it will be too hot. But for this one, that doesn't matter much. But you see this piece? I got it.
I want to frame it.
You want to frame it, eh? That's your first job. So you see the dross that I was talking about. It's minimum, yes. But to minimize this, two ways. Ideally, if it's already cutting through, then I don't need to increase the power. But I can increase the speed. Do you get it? Or I can also drop the height, the initial height. Do you get me? Let's try to do the same job just next door right here. Or I'm going to show you something. What's going to happen is, listen, your thing is very sensitive, right? So the moment it just feels like I don't have enough material, it's going to immediately give you an arc error. So that, listen, something is wrong here. Do you want to return? Okay. So here when it says you want to return, it's saying, do you want to come back to the origin position? So if I say yes, then it comes back to the 0 position. I just want to fix one thing to make sure that it doesn't off arc before M08. It's fine, I'll leave that. I can check time IHS. I told what to say. Okay, no, that's fine. Let's leave it there. All right, cool. You see? So this is basically the machine just showing you like, hey, this is the area that I'm going to cut in. If you're happy with that, then you can start your job. So it's simply asking, do you want to go back to the origin position? Okay, cool. Start. I don't know. Let's find out. Read your screen. Read your screen. Just think. Yes, there we go. Yeah, IHS is going to be able to see why it's doing this. It's sensing that I'm already touching the material with the electrode. So it's going to give you an arc error. So how do you fix this? IHS or changing where it's doing this, the IHS. Do you get what I mean? Because as long as it's doing it in here, it's wobble. So you want to bring it to solid. You can drop the height to be able to see better. Like even with this, just so that you can see what's up. Yeah. Okay. Now zero it from there. Yeah. Try to test your. Yeah. This. Okay. Cool. It goes up and down. All right. Cool. Try to raise the. You just try to raise it a bit. Now bring it to 30. You just want to make sure that there is a gap after it senses. There's no gap. Keep increasing it until there's a gap. Press it. Again, you need a gap. Drop that's a bit too much. Just drop it maybe to 43, thereabouts. Okay. That's fair. Let's start. So you get it, right? You see where the arc error was coming from. That feedback loop there, which it doesn't know where it's from.
I think you need to go faster here.
Certainly. I think that's the next thing we need to look at. Okay, Jackson, we're cutting through on 30. We have a bit of dross on our underside. What can we do to, first of all, to maximize production? We can go fast as we can, but to minimize the dross, we can increase the speed. Let's top up the speed and do the next cut on next to this thing.
And I can see here, it is cutting so much. Power is too much.
Power speed. Basically, it will cut this. Any time it's going to pass through here. Yeah, but yeah, I get, because remember, you want the power to be powerful enough to go through. Otherwise, if it just ends inside here, then that means you're not getting a clean cut. Yeah. We do slide. This guys can continue. You can talk to me. This guy can continue. Right, so basically, we've talked about the plasma cutter here. You're looking at metal cutting. So basically, you're looking at metal cutting with a plasma cutter, right? What you're looking at is basically cutting anything that is a conductive metal. So you cannot, of course, do any composites which have plastic inside them, like your die bond, you won't be able to do that. But anything metallic, anything that conducts electricity, you can do it on the plasma cutter. So your mild steel, your stainless steel, all of that, you can go for it. The main idea with CNC plasma cutting, again, as we talked about, is simply making sure that you have enough air, you have the right electricity, you have the right height on top of the material, and you have the right amperage and speed for the thickness of the material that you're doing. Now, what can you do with a plasma cutter? Plenty. Anything that means you're cutting your metal to size. You're looking at car parts, you're looking at mining excavator parts, you're looking at furniture, you're looking at anything that just needs your metal, cut to size. Enjoy. Top up the speed. Yeah, max it. Go to 3,000.
It's too slow. You put on a hot corners.
That's where we're going. That's the next thing I'm going to explain to you. You always want to think through this. When you're making your designs on a plasma cutter, you want to minimize corners as much as you can. Corners. Um, you see this thing? You think the corners are smooth simply because it didn't cut. Yeah. But as long as it would turn, it means that, remember, this thing is moving at 3,000 millimeters per minute. And then it gets to the corner. It's supposed to stop so that it starts again. So anytime it's stopping, all of that heat simply stops, then it reorients, turns the beam back on. So it will always leave a dent on it. That's why normally what we do is we put chamfered corners so that it just slows down, then it turns, and you have a finer cut. That's part of what you implement in your design. Okay, let's go. Max speed 3,000. Let's try it on 3,000. You want to change the starting position. There we go.
I know AM should take you back.
Hey,
That's why no small points.
no, all of this they wouldn't know. But as any company, I think a lot of the guys who do technical, they never do production, so they don't know. So that's the maximum speed. I don't think it can go beyond 3,000 that you can move with. You can exit here. Yeah, but definitely, that's the whole point. Yeah, this was a much better cut. Faster as well. All right, so we're clear. Let me give you one tip. You might get some material which has a removable coating, like a plasticish kind of coating. As long as it's metal, you can cut it. But try as much as you can to remove the coating on the top and at the bottom. The coating actually absorbs a lot more heat than the metal. You'll be surprised. It causes a lot of dross. Coatings actually, so you might want to minimize that. So what we're going to do is, while we're designing, I'm going to get the software part now. I need someone to at least put the new sheet so that we make a design there to come in.